The next team to present is the Succor from USM.
A very good morning to the panels, ladies and gentlemen. My name is Wei Huai, Mr. Tan Wei Huai. He is Kwok Meng Jong. We are from University Science Malaysia. Our area of interest is in renewable energy and environment. And as we know that according to the one research that everyone has well known, the International Energy Agency, in year 2012, the world has consumed 13 gigatons of energy, and we are expecting it to grow as the year goes. So as for Malaysia, we have consumed 47 megatons of these tons of energies, and 33% of all this energy consumed is rejected to the environment. That means there is no further action has been taken, and for 60% from these 33% are low quality of heat. We will define low quality of heat, which means is lower than 220 degrees Celsius. So whatever things of the exhaust or the waters that's below 220 degrees Celsius, we will say it's a low quality of heat. So as we know, Malaysia is the second world largest product over commodity over Indonesia in palm oil industry. We have the annual capacity of 105 million tons of FFB, fresh fruit bunches. And for these 105 million tons bunches, we produce 68.25 tons of palm oil main effluent and 23.52 million tons of steam exhaust from the sterilizer. So after calculations, we found that the heat energy available for us to harvest is 2.785 tons of energy, which we call TOE. So for this, we would like to suggest that to implement a system, you can see at the steam exhaust after the sterilizer and after the sludge pit, before it enters the cooling tower, we would like to suggest to implement a Stirling engine, a modified Stirling engine, as you can see on the table. With this modified Stirling engine, we can produce our own electricity, and we can reduce the carbon print that is being produced by the palm oil mill. So with this, we would like to suggest using working fluid R123 with boiling point of 27 degrees Celsius. And you can see this is the heat exchanger. This is the flywheel that will act as a temporary energy storage that will store the energies. And for this heat exchanger chamber, there is one more tube inside of it, which will make of copper, will help us to transfer the heat. And by using the temperature difference between this polymer and steam exhaust and our working fluid of R123, it will react and produce electricity. So it will start to move. So all these concepts are actually based on the PV diagram. If you are familiar with us, this is a thermodynamic cycle PV diagram. This is how the things work. So next, I would like to present a little bit more about the working principle, how actually the things work. First, you see at the red arrow, the polymer and the exhaust steam will enter to the heat exchanger. So the heat exchanger, it will boil the working fluid R123 with boiling point of 27 degrees Celsius. So with that, the pressure will increase as constant volume. Next, you will see this piston has been pushed upwards. Because of the pressures, then the gas starts to expand. The working fluid of R123 starts to expand. So it will have more volume and it will push the piston upwards while we maintain at a constant pressure. The next, we will have a stream of cooling water to enter from the top, and at a constant volume, the vapor reject to the cooling coil and reduce in pressure. And the last step, is at a constant pressure, the volume will decrease, and you see the pistons, or we will say is the diaphragm, they will be pushed, they will pull downwards, and it's a concept that the diaphragm will move up and down. By moving this up and down, we can produce electricity. So we like to show this.
So this is a conventional Stirling engine, which the working fluid is gas. But this conventional Stirling engine currently using in the industry is very costly because it needs 100 to 200 bar of pressure and 700 of degrees Celsius of heat source to keep the flywheel moving. But so we come up with this new modified Stirling engine so that we uses the theory of latent heat vaporization. When the liquid vaporizes, the change of volume is big, so it can increase the pressure inside the closed container and then move the Stirling engine to to generate electricity.
All right, next, let's take an example. How big is this engine going to be? So assuming with a length 0.5 meter, height of 0.16, 0.21 depth, by our calculation, we are able to produce 2.14 kilowatt. And the cost that we estimated to spend on this for the first prototype will be slightly costly because it's not yet commercialized, it's a new ideas. It will cost us up to 50,000. And through the calculations of return on investment, we are expecting to get the investment within 7 years. So after 7 years, it will be profit, and it's very minimum maintenance is needed because it's a closed cycle. There's no external heat supported to the system. Everything is going to work itself. Just like this is a water, we are using air as a medium. It will start to move, the wheel will keep on moving. So last but not least, the impact for this idea is to reduce costs and to save the environment by reducing the carbon print. That's all. Thank you.
From let's say 60 ton per hour mill.
Let's estimate the mass flow rate of the polymer to be 0.5 kg per second, and the heat capacity is 4.3 kilojoule per kilogram. So if we continue with this calculation, we can get 2 kilowatt. That means if we harvest, if that means in a 90 meter ton per hour of the polymer mill, and we harvest all the waste heat from the polymer from 90 degrees Celsius to 50 degrees Celsius, we can get
While he's calculating, actually this size of engine, right? If you have you have multiple the number of units or engines, or you make it in bigger size, the power output will be bigger. So right now, with the technical constraint, we are unable to test run on it because we are only ideally saying it works. So we still don't know whether how much heat loss actually we should anticipate in this case study yet. So but however, we'll still continue with this research, no matter how is it today. So we are expecting to have, take your time. Maybe we can move on with next question first, then later he can answer.
Have you worked try this on the Alpam factories?
No, this is, so far no, because it's a new idea that it's very hard to find a palm oil mill to let us to actually to install these machines at the sterilizer steam exhaust. We need a pipe, we need a pump, we need some valve, we need a storage tank.
But according to your calculation, is doable. Meaning
Yeah.
It's doable. It can be harvested in another way.
It definitely can be harvested because low quality of heat is very seldom harvested because the cost is very high. Because you need to use R123 and the cost of R123 is high, but we think that it's able to recover.
If we run the mill 10 hours and we have 3 gigajoule of energy, if you can harvest all the energy from the low quality waste heat. Gigajoule. Gigajoule, mega is 3,000 mega. If we manage to harvest all the energy, but practically it's not going to. Maybe because the Stirling engine, it works based on the transfer rate of the heat. That means the better the heat exchanger, the faster the heat transfer rate, and the engine will move faster. Then we can get more power. The problem now is if you want to harvest all the energy, we need to have a very large engine. That means if we have a small engine like this, we can only get 2.14 kilowatt, and that's small. But the engine is also small, but the cost is also small. And based on our calculation, we can, if the diesel engine costs 80 cents per kilowatt hour, that means we can recover in 7 years' time. And by the time goes by, the technology become mature. I think this is a technology worthwhile for us to explore, because waste heat is instead a waste, because we need energy every day. We produce it, we consume it, and we also waste it. I think it's good to recover the waste heat. I think if we do that, this is it's like a lead company to do this thing in the world, I think, industry.
Okay. Because, okay, from the industry point of view, all this while we have excess energy, or we have sufficient energy. But if we can harvest low quality heat for energy purposes, that means we can also put aside some of our biomass, palm shell, as well as fiber for export for other purpose. That
Yeah.
boleh jual lah.
Yeah, yeah.
And palm shell is now about 300 ringgit per ton, or 150, between 150 to 300 ringgit. So the value. for
Yeah,
us.
yeah, I get.
So I just want to know how much. Maybe later we can see how much we can produce from one mill and how much that in terms of value to us.
Yeah, sure, sure. We can share more about that later. Giga got 90 10 power 9. Yeah, right now, if you look at this cycle, the common one is ORC, organic Rankine cycle. You can see, yeah, this one. But the cost is very high, and you can see that the efficiency is only 5%. And this Stirling engine is the one that is nearest to the highest efficiency of engine that we call Carnot cycle. So we are actually targeting through this Carnot cycle. We have our own Stirling engine by using the PV diagram to give us the highest efficiency to recover the waste heat. Yeah, we don't need combustion. We're not going to burn something to get something. We're just fully utilize whatever has already comes out. Yeah, two things. We have two input. You can see from the schematic diagram that we have drafted. Okay, yeah. This is the steam exhaust from the sterilizer after we cook the fruits. And after the sludge pit, before it enters the cooling tower. In fact, after they pass by this Stirling engine, this polymer temperature will reduce to 50 degrees Celsius. And we are hoping to have another kind of impact that we might be able to, the possibility to eliminate cooling tower for anaerobic digestion. So we believe it's going to save some space and save some cost. But due to the current technical constraint, we cannot have very particular calculation on that. But we can assure that once it passes through this Stirling engine, the temperature can be reduced. So let's take polymer as an example. I believe if you work in a mill before, everyone, you know that polymer is always a problem because it's something not going to give you any money. And you need to dispose it with a correct BOD and COD. So we're thinking of having this. We can reduce the temperature of the polymer, and we might be able to eliminate cooling pond, cooling tower for anaerobic digestion.